Welcome to The Explainer. Today, we're diving into a really cool paper by P. Frauendorf. It proposes a pretty radical idea, asking a simple question. What if the best way to learn the most out-there concepts in physics wasn't to memorize them, but to actually discover them for yourself? I mean, just think about this for a second. How would you explain the feeling of walking, of gravity pulling you down, of your feet on solid ground, to a creature that's only ever known what it feels like to float in water? You can try to describe it, sure. You could show it diagrams, but it's just not the same as the real thing, is it? All right, Section 1, Learning Extreme Physics. This is pretty much the exact problem we face with what the paper calls extreme physics. The rules of the universe at unbelievably high speeds are completely, totally outside of anything we experience in our day-to-day lives. So how do we usually learn it? Well, we're told the answers. We're handed the equations that giants like Newton and Einstein figured out. But this paper argues that's just like the fish being told about walking. You're just getting a secondhand report of somebody else's incredible journey. And this quote, this gets right to the heart of it. When you experience something directly for yourself, you're not seeing it through someone else's filter, through their words or their preconceived ideas. You get to bring your own fresh eyes to it. And that, right there, is where real discovery can happen. So, Section 2, a playground for motion. What's the solution then? Well, the paper suggests we build a kind of virtual playground, a simulation that lets you get your hands dirty and experiment with these bizarre phenomena directly. The paper calls this a minimally mediated experience. Now, that might sound a little academic, but the idea is actually super simple. It just means we're stripping away all the complicated stuff. No fancy lab gear, no need for years of training. We're talking about using skills you already have, like spotting patterns, or even just the basic hand-eye coordination you'd use in a video game. Okay, so here's the setup. It's a simple virtual air track. First, you compress a spring. Then, boom, it launches a glider. That glider flies through a timing gate. After that, it smacks into and sticks to a second glider. And the new, heavier combo goes through a second timing gate. And that's it. Just simple cause and effect. Section 3, Case File, Flexible Spring. All right, this is where we get to put on our scientist hats. Case file number 1 uses a totally normal, flexible spring. One that's going to create speeds that feel familiar, like things we see in our everyday world. Let's look at the evidence. Okay, here's our data sheet. There are 2 clocks we need to watch very closely. T is the lab clock. Think of it as stationary, just watching everything happen from the sidelines. But tau, that's the Greek letter tau. That's the traveler's clock. It's actually riding on the glider, experiencing the trip firsthand. So take a close look at the data from gate A. Compare the lab clock, TA, with the traveler's clock, tau A. What do you see? Do you notice a pattern? Are they telling the same story or different ones? And what do we find? Well, they're almost a perfect match. I mean, look here. When the lab clock says 6.15 seconds, the traveler's clock says 6.13. When one says 0.31, the other says 0.3. Sure, there are tiny little measurement variations, but basically, the clocks agree. This makes total sense, right? It matches our intuition perfectly. So far, everything is normal. Section 4, Case File, Tight Spring. Now for the fun part. We're swapping in a much, much tighter spring. This thing is designed to launch our glider at absolutely incredible speeds. We're talking speeds that start to get close to the speed of light. And here's the data from that experiment. Right off the bat, you'll probably notice the times are now in nanoseconds. That's billionths of a second. So yeah, we are moving incredibly fast. But now look closely at the lab clock and the traveler's clock again. Something has definitely changed. Those 2 clocks, which were perfectly in sync before, are now telling 2 very different stories. What is happening here? This is the central mystery we need to solve. And the difference is staggering. I mean, it's huge. At top speed, the lab clock measures 1.11 nanoseconds for the glider to pass through gate A. But the clock that was actually on the glider, it only measured 0.466 nanoseconds. The traveler's clock is running dramatically slower. Let that really sink in for a moment. Less than half the time has passed for the moving object compared to the one that's standing still. You are seeing Right here in the raw data, a fundamental rule about how the universe works, and it's completely alien to our everyday lives. So, Section 5, discovering the rules yourself. And that's the whole point. This isn't some error in the simulation. This isn't a mistake. By just looking at the data, we have just made a profound discovery. What you just saw is a real phenomenon called time dilation. It's one of the core ideas of Einstein's theory of special relativity. But instead of just being told that moving clocks run slow, you saw the proof for yourself. You discovered it in the evidence. And by doing that, you've basically placed yourself at the end of a very long, very important story. You've got Aristotle, Galileo, Newton, and Einstein all trying to figure out the rules of motion. And today, right here, with a simple simulation, you've become a part of that story, uncovering the same puzzle piece that Einstein himself did. And that's really the ultimate takeaway, isn't it? The author says it best right here. When you figure this out from the data itself, that little bit of cosmic understanding isn't just a fact you memorized. It becomes yours. You earned it. So why does all this matter? Well, because it takes something famously abstract and makes it feel real, makes it intuitive. It changes your role from just being a passive student to being an active discoverer. It proves that you don't need a PhD or years of intense math to start playing with some of the biggest ideas in the entire universe. You just need a playground and your own curiosity. And that kind of leaves us with one final big thought. We've just seen how a simple, almost game-like experience can let anyone peek behind the curtain of reality itself. It really makes you wonder, if the secrets of space-time can be found with just a few clicks, what other profound truths are out there, just waiting for someone to find a new way to look at them?